Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Schuller at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this notebook we'll talk about convolutional autoencoder. So let's get started. A so-called autoencoder is a neural network with unsupervised training, which means that we don't need to supply a target function. There is only a training set, which is also the target set. A convolutional autoencoder uses convolutional neural networks. An autoencoder maps the input signal to a lower dimensional representation using its encoder part. In this way, it is similar, for instance, to an audio encoder, which compresses an audio signal into a representation with fewer bits than the original audio signal. I invite you to take a look at another course offered by Professor Schuller at the Ilmenau University of Technology. It's called Audio Coding. We also have many Jupyter notebooks and tutorials that you can find here on the GitHub and on a YouTube playlist. The decoder part of an autoencoder maps the lower dimensional representation back into the higher dimensional representation. And this is similar to an audio decoder, which decodes the compressed version back to an audio signal. The reconstruction after the decoder part should be as close as possible to the original. Hence, the original training set is also the target. In our Python example, we simply use a 1D convolutional layer for the encoder, and this corresponds to the analysis filter bank of an audio encoder. And if you're interested to know about analysis filter banks, synthesis filter banks, and filter banks in general, we also offer a course. It's called Multi-Rate Signal Processing, offered by Professor Schuller at the Ilmenau University of Technology. And you can find, again, Jupyter notebooks with interactive examples and embedded video tutorials from our YouTube playlist. But going back here into this Python example, where we use a 1D convolutional layer for the encoder, we also use an activation function. And in this case, we use the 10H function, which seems to work better than the sigmoid in this application, probably because it keeps the signs. We will use a stride or a downsampling factor of n equals to 1024 and filter kernels of size 2 times n. To obtain the same dimension as the input at the encoder output, which is a critical sampled filter bank, we need n filters or n output channels. But because we want to reduce the dimensionality after encoder, we choose a lower number, which makes it an over-critically sampled filter bank. For instance, with out channels equals to 32. This is similar to an audio encoder, where we simply drop the filter subbands with the highest frequencies. We will still have to choose the padding, meaning the number of zeros which we pad before and after our audio signal before the convolution, or rather correlation in PyTorch. To align the output of the decoder with the input signal for the case of symmetric filter kernels or impulse responses, we need a padding of the filter length divided by 2 minus 1, or the kernel size divided by 2 minus 1, because then the filtering starts with the first sample at the center of the filter, which corresponds to the position where the filter outputs the corresponding filter sample for both encoder and decoder. Hence, in Python, our encoder convolutional layer becomes this here. So we will have the number of in channels equals to 1, the number of out channels equals to 32, the kernel size equals to 2048, so it's 2n. The stride will be 1024, and padding will be the kernel size divided by 2 minus 1. and we use bias equals to true. Observe that we have one input channel, the audio signal, and 32 output channels, the subbands. For the decoder part, we need a synthesis filter bank, which in neural network literature is also called a transposed convolutional layer. And in PyTorch, we can use the conv transpose 1D. Therefore, we will have our conv transpose 1D that has in channels equals to 32, out channels equals to 1, the kernel size equals to 2048, the stride equals to 1024, and padding equals to 1023. So we can see that it's the same kernel size, the same kernel, and the same padding as we used for the conv1D. Observe that for the synthesis filter bank, we have 32 input channels, the subbands, and one output channel that will give us the reconstructed audio signal. The function for the encoder is now given here. So we will have our conv1D layer given here that we're calling conv1. Then we will use the 10H like we mentioned before, and then we will return the output. Observe that here we included the 10H activation function, which can also be seen as a range limiter between -1 and 1. For the decoder, we have this function here, where the X reconstructed is the synconv1 that is defined here as using this conv transpose 1D. For both together, it becomes the overall autoencoder. And we have the encoder, the decoder, and we will have the output is the reconstructed signal. We will put these functions into a class called conv autoencoder. For the training, we use the input signal also as a target. There, we have to limit the length to the signal length produced by the output model, which we can simply obtain by letting the model run once before the training. Here, y is the target signal with the same length as the output, the model output. As a loss function, a common choice is to use the mean squared error, even though it might not be optimal, but we will try out in this example. The training then can be done in a for loop, and we have a certain number of epochs, and then we will have the predictions generated by applying the model to our input. We calculate our loss, then we will just print the loss every epoch divided by 10, and then we will also need to, in every step, to use the zero grad into the optimizer. We use the backward to the loss, and we use this step into the optimizer. Here we have our full Python code. So first we will import the Python packages we're going to use. As usual, we are going to use PyTorch. We'll use matplotlib pyplot to plot. We use librosa to handle audio, and numpy for other array operations. We can also use a GPU or a CPU. So if you have a GPU, or if you're running this using Google Colab, you can set your environment to use a GPU, and then you can run everything using the GPU. Another auxiliary function that we've been using before is this function to convert a signal vector X, like for example a mono audio signal, into the tensor prepared for the convolutional layer of PyTorch. Here is the class conv autoencoder that we mentioned before, where we set our layers. So we have the convolutional one-dimensional layer, we have the convolutional transpose one dimension, we set our encoder, our decoder, and then we have the forward that puts together the encoder and the decoder. Now we can load an audio, and in this case I'm going to use the legendary rock and roll AC/DC introduction of Back in Black, and we will use a stereo file that one channel, for example the left, will be used for training and the right will be used for testing, for example. So I am loading using Librosa, then we are normalizing, so we have the amplitudes going from -1 to 1, and then we're applying our signal to PyTorch, and we have an X-train and an X-test that we're going to use later. Now we are generating our model, and we have here the loss function, that is the mean squared error loss. We also have the length of the signal at the output of the network. Then we set the target signal with the same length as the model output. And these are the parameters that we have. We generate our models, and we will have a total number of trainable parameters. We will have the length of the output, then we set so the target and the input, they have the same length. Next, we set our optimizer, and we are going to use an ADAM with the learning rate starting with a 1 e to the power of -4, and then we can also save our weights that we've been doing before, but here we're just training using the X-train that we defined later, and as I explained, there is this for loop, and we go in using 10,000 epochs. So now the model is training, and we can see that it starts with the loss function very high, equals 0.01, and then it goes down to as low as 0.027 something. So after our model is trained, we can read the obtained weights, and we can also plot the encoder analysis filter and the decoder filters for subband 0, and also the encoder and decoder filter coefficients. And this is what we have here, the encoder and decoder filter coefficients. Then we can test our model on a training set. So we will have the predictions by applying the model, the training model, with the training set. And this way we have our predictions. And then we will have here the comparison between the predictions and the target. And this is what we have here, the target and predicted signal for one batch. Finally, we can listen to the result of the reconstructed signal. And it goes like this. So you can observe that there is a difference, an audible difference between the original file and the reconstructed, and it's clearly noisy. So in this way, the autoencoder can be seen as a kind of a filter. It learns a low-dimensional subspace from the training set. Every new input is mapped onto this subspace. And if it doesn't quite fit onto this subspace, major elements might be missing. So now if we apply the same model to the test set, so we split our original, it was on stereo, we use one channel for the training. Now we will use the other channel. We'll have predictions from this other channel, this X-test, and we will also compare the predictions with the target. And this is what we have here. And we can also listen to it. and you clearly perceive that the reconstructed signal is much more noisier than we used with the training set. So the model was trained using this X-train data set, which was one channel of the stereo audio signal that we had. And now if we're applying the same model that was trained only onto this training set, we apply a different input to the model, and we see that the output of the reconstructed is much more noisy. So we can clearly see how we train our model, it influences in terms of generalization to other signals. One more thing that we'll look at is the effect of signal shifts. So observe that the stride we used in our autoencoder. The stride corresponds to the down and up sampling rate of the corresponding filter bank. This sampling together with the convolution has the effect of processing the signal in blocks of size of the stride. If we now shift our input signal by prepending the number of stride zeros at the beginning, hence delaying it by stride samples, we will get the same blocks just one block later. On the other hand, if we prepend a number of zeros which is not an integer multiple of the stride, the blocks will look different, and hence the result will look different, not just shifted. So for this example, we are going to test the trained autoencoder first with 100 zeros added at the beginning of the training signal. And we are using this constant pad 1D, so we are inserting 100 zeros on the beginning of this training. So we are giving a shift of 100 zeros, and then we are making predictions from this shifted input signal, and we can listen to it. We notice that the output appears really noisy. We will now shift not by 100 but by 1024, and this is related to the exact same number of strides. So we are now in this situation that we are shifting the input signal by prepending the number of stride zeros at the beginning, that is delaying it by stride number of samples. And this we are going to also listen. Well, let's compare. So pay attention now that we are using the same X-train. So both use the X-train, but first we are shifting by 100, and here we are shifting by 1024. And when we use the 1024, which is the same number as the stride, we notice that the noise added is much less. So we clearly see the effect of having these blocks starting on different points, how it affects the output of our model. So this behavior might be desired if a certain position or timing is important, but often is not desired. A straightforward remedy is to set stride, for example, with 1, but this leads to a much higher computational complexity for training and test or inference. As a compromise, we reduce the stride to a small value. For instance, for example, a stride equals to 16, and this has a lower complexity and not much audible shift sensitivity. And you can experiment if change in our model, you change the stride value both in the encoder and both on the decoder. So when we define our model here, if you change the stride values here, and you can change to two different values, for example 16, and then you compare and see what happens.